In data analysis, the tools and methods to analyze the data are usually divided according to the number of variables under analysis. When we refer to univariate data, study is focused on only one variable. For example, here we have the height of people in a particular population. When we refer to bivariate data, the study is focused on the relationship between two variables. Here, for example, we have the height and weight of people in a particular population. When we refer to multivariate data, the study is focused on the relationship between multiple variables. For example, height, weight, age, and glycemia of people. So, bivariate data is also an example of multivariate data. Some of the most important concepts related to the univariate data analysis are the average, mean, mode, and median, and the statistical measures, variance, standard deviation, quartile, percentile. Some of the most important concepts related to the bivariate data are the covariance, covariance matrix, correlation coefficient, and correlation matrix. The average is the concept related to finding the central value of a set of numbers. There is a number of ways to find the center based on different criteria. In the arithmetic mean, all instances in a particular dimension are added together and divided by the number of instances. The average of all instances in X is denoted X bar. In the geometric mean, all instances in a particular dimension are multiplied and then we compute the nth root of the result. In the harmonic mean, we have a sum of the inverted value of the instances and the result is multiplied by n. Let's see some examples of these different ways to compute the average. Here we have some sets of points. Linear, subsets with different values, increasing exponential, decreasing exponential, and with positive and negative outliers. Here we can see the values of the arithmetic mean, geometric mean, and harmonic mean in each case. The arithmetic mean of values between 1 and 10 is 5.5. The geometric mean of the same values is 4.53. And the harmonic mean of the same values is 3.41. There is a significant difference between them. We can observe the same in this case. In exponential values, the behavior is about the same, but we can observe that the difference between the three means is more pronounced. Particularly, we can easily observe that the harmonic mean is always in favor of the smaller values. When we have the outliers example, we can observe the same behavior. Some important remarks about these means. All three means are always between the minimum and maximum values of the set. The value of the arithmetic mean is always bigger than or equal to the geometric mean, and the value of the geometric mean is always bigger than or equal to the harmonic mean. So, in practical situations, we can conclude that arithmetic mean gives the same significance to all values. Geometric mean skews slightly to the lower values. Harmonic mean skews hardly to the lower values. But there are other ways to compute the average. One is the mode. The mode is the most frequent occurring number in a list. In this example, 4 is the most frequent value. The other is the median, the middle number of the group when they are ranked in order, or the mean of the two middle two if there is an even number of numbers. In this set, we have 9 ordered numbers. The fifth element is the median. Variance is the measurement of the spread between numbers in a dataset. It measures how far each number is from the mean. There are two ways to compute the variance of a set. The variance of a population is given by this formula. Squared sigma is equal to the sum of the squared distance of all points to the mean of the population divided by the population. However, if I'm computing the variance of a sample of the population, squared S is equal to the sum of the squared distances of all points to the mean of the sample set divided by n minus 1. This n minus 1 in the formula occurs due to the Bessel's correction. Suppose that we have 25,000 measures of the height of all the students in a university, for example. The mean of the height is 1.72. And the variance of the population, here divided by n, because this is the population, is 0.0023. Now, suppose that I have a lot of samples of this population. Here I have 500 sets, and in each set I have 50 samples of this population. Well, in each set I can calculate the mean and the variance, and the mean and the variance of the sets are not exactly the same of the population. If I have the means of all sets, my best estimation of the mean of the population is the mean of the means. In fact, the mean of the means is 1.72. However, if I compute the variance of each set dividing the value by n, the mean of the variances is not the best estimation of the variance of the population. Instead, if I adopt the Bessel's correction dividing the value by n minus 1, this is a best estimator of the variance of the population. In this example, with 5,000 sets, with only 5 samples in each set, the difference is more pronounced. The variance of a population must always be divided by n, while the variance of the samples must always be divided by n minus 1. The standard deviation also measures how far numbers are from the mean, but in the same units as the mean. The standard deviation of a population is given by the square root of the variance, and in this case the variance is divided by n. The standard deviation of a sample is also given by the square root of the variance, but in this case the variance is divided by n minus 1. The smaller the standard deviation, the closer are the points of the mean. Quantiles are cut points dividing the range of a probability distribution into contiguous intervals with equal probabilities. In quartiles, there are 3 cut points that will divide the dataset into 4 equalized groups. The second quartile, Q2, is the median of the data. The first quartile, Q1, is the middle number between the smallest number and the median of the dataset. The third quartile, Q3, is the middle value between the median and the highest value of the dataset. The pth percentile of a list of n-ordered values, sorted from least to the greatest, is the smallest value in the list such that no more than p% of the data is less than or equal to that value. Covariance is a statistical measure of the joint variability of 2 random variables. The covariance of a population is given by the sum of the distance between each element of the X population to the mean of the X population, multiplied by the distance between each element in the Y population to the mean of the Y population divided by the number of examples in one of these sets, remembering that the number of elements in both sets must be the same. The covariance of a sample is given by the sum of the distance between each element in the X set to the mean of the X set multiplied by the distance between each element in the Y set to the mean of the Y set divided by the number of elements in one of these sets minus 1. Here we have some examples of bidimensional data sets and the value of the covariance to this data. Some remarks. If variables tend to show the same behavior, covariance is positive. If variables tend to show opposite behavior, covariance is negative. The larger the covariance, the stronger the relationship between sets. Covariance has no defined range, minimum or maximum values. We can't compare covariance over datasets with different scales or different numbers of elements. Covariance matrix or dispersion matrix or variance-covariance matrix express the joint variability in multivariate data. Suppose that we have three variables, A, B, and C, each of them with n observations. So we can compute the covariance matrix between these variables. The covariance matrix can visually indicate when two of these variables have similar behavior. Some remarks about the covariance matrix. The diagonal of the matrix stores the variance, since the covariance between A and A is the variance of A. The matrix is symmetrical about the diagonal, since the covariance between A and B is the covariance between B and A. The Pearson Product Moment Correlation Coefficient, PPMCC, or just Pearson Correlation Coefficient, PCC, is another numerical measure of the correlation used to analyze bivariate data. The correlation coefficient used for population, or the correlation between X and Y, is given by the covariance between X and Y divided by the standard deviation of X multiplied by the standard deviation of Y. The correlation coefficient used for samples, called R, is given by this formula. Unlike covariance, correlation is limited to the range between -1 and 1. So, it's more useful for determining how strong is the relationship between two variables. It is also not affected by changes in the center of scales or variables. Here we can see examples of the correlation coefficient for different ranges of bivariate data. The correlation matrix is a matrix showing the correlation coefficients between sets of variables. The diagonals of this matrix are always 1s, since the correlation between A and A is equal to 1. Also, the matrix is symmetrical about the diagonal, since the correlation between A and B is equal to the correlation between B and A.